All right, what's up, class? So this is, I don't know how long this video is going to be, but essentially what I'm going to do here is I'm just going to go through the homework 1, homework 2, and the quiz. I'm going to go over all the answers very briefly so that you guys just have an understanding of how to solve these. Right in red. All right, now, so there will be timestamps that you guys can just follow. All right, so jumping in, I'm going to start at number 1. All right, so this is for number 1. Now, it says describe the physical characteristics that distinguish a fluid from a solid that is not. So that grammar may be a little off. So a solid that is not a fluid, right? It says to describe the property of flow as well as their molecular structure. So essentially, a fluid and a solid are different because a fluid has laminar and turbulent flow, right? All the particles are free to move around so they can flow. All right, so can a gas. You can have a stream of gas coming out of, a propane tank. And so that was one of them. The other half is the molecular structure. Solids are rigid because their molecules do not move that much, right? Whereas fluids, their molecules can interchange places between each other at any given moment in time, right? So it's entirely dependent on their molecule movement and velocity, as well as whether they can freely exchange between one another, right? Okay, so that was number 1. And number 2, how would pressure relate to the ability of a knife to cut things? Well, essentially, this goes off and back to Pascal's equation, which is P equals F divided by A. Now, the importance of Pascal's equation is here. Okay, is that, you know, uh, it's a relationship between force and area. So what makes a knife dull or sharp, and how does pressure relate to that ability? Well, everything has something called tensile strength, which is, a material's ability to hold itself together when applied with the pressure, right? So when you apply a pressure to, let's say, a fabric has some specific tensile strength, well, you need the same amount of pressure to cut that fabric when using any object, a finger, a knife, all the same. So what makes a knife dull or sharp is the area, because if you have a lower area, you can get the same output of pressure with lower force. So that's why it's easier to cut things with a sharper knife that has a sharper area, is a thinner blade, right? If you want to look up something cool, an obsidian blade can actually have a 1 atom width, which is technically the sharpest thing that is known to man existent. Right? Unless you can get another object with a 1 molecule width or 1 atom width that's smaller. Right? But I digress. Okay, and then number 3 says describe why a dull needle would hurt more than a sharp needle when getting shot. Well, that's mainly because a dull needle has more surface area. So because you have more surface area, you need to apply more force to have the same amount of pressure to pierce the skin, right? And because of that, a sharp needle needs less force. Now, the force determines how much pain we experience because our receptors in our bodies are force sensitive, right? Therefore, a dull needle would hurt way more because you have to apply more force, right? Now, moving on to number 4, why is it easier to float in the Dead Sea, which has high salinity? For this one, we're going to use Archimedes' equation. This has FB equals rho v and g. So this is going to be rho. It doesn't look too much like a rho. It looks more like a p. So I'll rewrite that. So rho vg. Right now, high salinity. Salinity is dissolved salt in water, right? And the dissolving of salt does not increase the volume of water if you go try it in a cup right now. So therefore, volume doesn't change, and therefore the mass in the water changes. So therefore, the density of the fluid is getting higher. Salt water is more dense than normal fresh water. So therefore, the rho in F equals rho Vg is increasing. Therefore, the buoyant force is increasing. So when you're on the surface, when you're on a surface level, there's a higher buoyant force generally. So therefore, it's easier to float. Right. But number 5, would it be easier or harder to swim inside of the Dead Sea? Explain the reasoning. It'd be harder because now we're talking about inside when you're submerged. Archimedes' equation does say that when you're submerged in something, the buoyant force acts all around you. Therefore, when you have that buoyant force acting all around you, that's why in the Mariana Trench at the bottom you get crushed, right? The deeper you get. Therefore, it's harder to swim because there's more force acting upon you and you have to move a denser fluid. It's harder to move a denser fluid. Just like you could look up an experiment where someone's swimming through maple syrup. I think I saw that video just a while back. Right now, moving on to number 6. I'll let you guys read that problem on your own, but it's basically saying, can you swim in zero gravity? right? Well, astronauts make it look like you can swim, but can you swim in water in zero gravity is basically what this question is asking. Now, it says to write the equation for buoyant force right here. That's Archimedes' principle, right? And it's saying in zero gravity, right? So if what zero gravity means is just zero G's. If this becomes zero, everything in this side of the equation also becomes zero, and buoyant force becomes zero as well. So you can't swim in water on the ISS, but you can swim through air, right? Number 7, when a bathtub is full of water, it is difficult to pull the plug. Why is this? Well, we have to write out the relevant equations, which for this one is going to be continuity. So this v with the hat over it is going to be velocity. A2, V2. I'm trying to write with a mouse, so excuse it if it looks kind of off. All right. So, and then the other last one would be Bernoulli's equation, which is P plus rho V squared over 2 plus rho GH equals C. C stands for constant here. It's just any number. It's just a number. That number depends on the fluid and the scenario. So that's just going to be constant. Okay. Now, when a bathtub is full of water, it's difficult to pull the plug. Why is this? The explanation for this is a mix of Archimedes' principle, because at the bottom, the pressure is going to be the highest because there's a high amount of force, right? Buoyant force acting down on it because there's nowhere else to go. It can't just be pulled up. And A1 V1 equals A2 V2. That hole, when you pull it, it's going to want to have a high velocity, right? That high velocity is what contributes to low pressure, right? In Bernoulli's equation. So when that bathtub water is flowing, that water is exerting a low pressure on the pipes around it, right? But when you pull it up, the Archimedes principle says the buoyant force is going to be acting down upon it very hard at the bottom, right? So you have to differentiate that pressure gradient, or you basically just have to overcome Archimedes' principle and pull up water that, like, the entire weight of the bathtub's water, right? So that's basically why number 7 is how it is. Number 8 is an interesting thing about ducks and geese is that their feathers and feet are waterproof and they have greater density in the water. However, they don't sink. Explain how this occurs. Well, if you know about a duck, it's basically fluffy, right? And this is the same principle about how bottles float, right? A bottle floats when it's empty because the volume of the glass is that the volume the glass is taking up in water is really high compared to the density of the glass. So therefore, it won't sink. However, the moment you put water in that bottle, right, then now the bottle's overall density is heavier than water. The water's trying to float on. So therefore, boom, you're unable to float. Right now, how does this apply to ducks? Well, ducks also keep air in between their feathers, and their feathers are hollow. They're not very dense things in general, but because of that volume, they're able to exceed the um, the threshold to float, right? So therefore, they just float. But why is this question important? It's because their feathers and feet are waterproof. How does that have to do anything? Well, remember how I said if you put water inside the bottle will sink, right? The duck doesn't allow water to enter it and stays, airy. Airy, is that a word? It stays filled with more air, so it doesn't sink. Okay, now look at the image below. It shows a common household faucet. There is a tube extending above the faucet filled with air that serves a very useful purpose. When water attempts to backflow, the air will be sent and the water can flow forward. All right, explain how this occurs with Bernoulli's principle. Now, this occurs because when the water is flowing, right, it has a low pressure, right? The pressure is low. And the air doesn't exert as much pressure as water would because of the density of the fluid, right? Air is less dense than water. So they're both low pressure, right? So they don't really go anywhere. But when the water wants to backflow, it has to stop momentarily, right? Like if you want to reverse a car and you're going forward, you have to stop and then kick it into reverse at some point. You got to stop. So once that water stops, that pressure grows a huge amount. So that means that there's a high pressure in this in the water tube, and it's exerting high pressure. And because of that, the air, which is exerting a low pressure, remember Poiseuille's law or Poiseuille's law states that any fluid flows from high to low pressure. So because the pressure of the water is higher than the air, the water is going to want to flow up, right? The reason it doesn't flow backwards is because there's more water there. It's just the same pressure. So it chooses to flow up, and then the air goes out, and it's what is it? It's different. So once the air goes out, let me do that green, the air is going to go out and down. Now this water from the back is going to want to go forward, right? It's going to want to go this way. So that's why it doesn't backflow. It just keeps going forward, right? That air pocket is pretty important, right? Then so that's literally why it doesn't flow back. And the main principle here was Bernoulli's principle, as the problem says. All right. On your exam, I won't have the same thing I did on the quiz where it was I told you which equations were relevant. I mean, it's because it's an online exam. I expect you guys to have, you know, you have those resources near you. You can use them. All right. Okay. Now let's move on to homework 2, the gas laws. I'm just going to write the gas laws right here on the side because I'm just going to go through this one by one pretty quickly. All right, so the gas laws, I'll write them in green. The first one, the only one that we have is PV equals nRT. Now you're saying, what about these ones, Mr. Cho? Well, these ones are just derivatives of the ideal gas law where certain things are kept constant, right? So for example, if I were to write Boyle's law, which is PV equals K, K means constant, right? So essentially, K is just nRT constant, right? And the number of molecules are constant and the temperature is constant, then it all, and the R is always going to be a constant anyway. So it all adds up to being 1K, right? And that's why it's PV. And so the form is pretty much the same, except, these three combined into that. And that applies for all the equations. So that's how you can see that. All right, now going through with the questions. All right, it says, what does it mean for a variable to be constant? Well, for example, temperature is constant in Boyle's law. What advantages does having a constant variable give scientists when they're trying to make observations? When something is constant, that means that it does not change, literally. It allows scientists to make observations better because once you have a constant variable, right, you can basically eliminate its change from that equation. So for example, if we kept temperature constant, then we can eliminate it from this equation and just be left with PV equals NR and see the relationship between them. If you have more things constant like pressure, then you get V equals NR, right? Which is literally Avogadro's theorem, right? Okay. So number 2, I'm gonna just skip over because essentially the answer is already given on the whiteboard that I taught this lesson on. And also these equations are derivatives of the ideal gas law, right? All right, so now I'm moving on to 3. What is the relationship between pressure and volume in Boyle's law considered an inverse proportionality? All right, so writing the answer to this, an inverse proportionality is anytime an equation looks like y equals k, which is a constant, over x, all right? And you're graphing y versus x, right? So anytime you're graphing y equals something divided by x, that's an inverse, right? The graph looks like this. All right, negative correlations graph looks different because this is negative correlation on the left here, right? Now you can see that this one on the right is bent, and that's inverse proportionality, right? It's way more important because it has something called asymptotes where, the efficiency of the decrease gets exponentially greater, but never actually hits 0. Whereas in negative correlation, at some point they could hit 0, right? So that's the big difference. All right. So, and then it says, describe what happened in the following situations relating to the ideal gas law, right? And then draw a graph. I won't draw the graph here, but I will just briefly mention what is going to happen. So 4. So this is for 4. Now A says pressure and temperature are kept constant and the number of moles increases. So I will, for reference example, I'll just do one of these. Pressure and temperature are kept constant and the number of moles increases. So pressure and temperature are kept constant. So let's rewrite this equation without pressure or temperature. V equals NR. All right, and number of moles is increasing, right? So if N on the right side is increasing, then V on the left side must be increasing as well. You can tell that because if they're on the opposite side of the equal sign, then they have to go the same direction. All right, so opposite side of the equal sign, same direction. If they're on the same side of the equal sign, like P and V, that's when they're inverse. They go in reverse directions. So that is an important factor to note, right? So that's how you solve all of these. So let's go through them all. Volume and temperature are kept constant, and the number of moles is decreasing, all right? Oop, that's a comment, that's my bad. So volume and temperature are kept constant. So these two, ignore these two, and the number of moles are decreasing, right? If it's decreasing, then they're on the opposite side of the equal sign, so pressure must be decreasing as well. Notice how I'm not talking about R. That's just because R is the ideal gas constant. It doesn't change. All right. Pressure and volume are kept constant. So these two are kept constant, and the number of moles are increasing, all right? So that means that temperature must decrease because they're on the same side of the equal sign, okay? All right, a little short water break. In the image below, an ideal gas has been trapped inside of a container with a movable piston, all right? So as you can see, the movable piston moving up and down changes the volume that the gas can occupy. What happened to the temperature of the gas is the piston was moved up and pressure was kept constant. So let's draw this out. If the piston was moved up, that means volume is increasing, all right? And the pressure was kept constant, right? So an ideal gas has been trapped, so therefore this is constant as well. So if volume is going up, then temperature must also be going up, right? Because they're on the opposite sides. What direction would the piston move if the pressure remained constant and the temperature of the gas was raised? So that means that this is still constant. So N is always going to be constant here. Pressure remained constant. So, and the temperature of the gas was raised. It's going to go up. That means they're opposite sides. Volume must also go up. So the piston would move up to increase volume. What effect would doubling the number of gas molecules in the container have if the piston was fixed in place? So V is constant. And what would doubling this do? So this is increased, right? So it would correct two possible correct answers. You could either say that pressure would increase because there's more gas particles, or the temperature would decrease. Right. The more likely candidate is for pressure to increase first. Right. Temperature changing is less likely to instantly occur, but both are correct answers in Mr. Cho's eyes. All right. Now let's move on to the quiz. So, like I said, these kinds of little things that tell you which equation to use, they won't be there unless it's a really difficult problem that you guys would have never seen before, right? So don't depend on it, but just know that, if you study and have the formula sheet, you will be set to go, right? Or, have this complete study guide next to you. So Zebi and his sister Zebiana are trying to make some curry for their dad. Okay, I'll spare you the story. It's essentially asking Zebi cut his finger and Zebiana cut her finger too. Zebi nicked his finger while Zebiana completely chopped it off, right? This is actually going back to what chefs say. Dull knives are a danger in the kitchen, right? That's because the sharp knife had lower area, right? So having a higher area, remembering from homework 1, higher area means that you need more force to exert the same amount of pressure. The vegetables all need the same amount of pressure to be cut. Therefore, Zebiana was exerting more force, and that force allowed the knife to go straight through her finger, right? If you guys ever have knives at your house, they're just dull and just unable to be used, right? Go get a sharpener. They have one of those grinding sharpeners. You don't need a whetstone. The way Mr. Just a small quick tip is the way Mr. Cho determines if a knife should be used, right? Should be sharpened or is not okay, right? Is can it cut a tomato? Like, can it cleanly cut a tomato? If you can't do that, probably no. Okay. All right, number 2, Darla is installing a new shower head. Darla said her shower head will provide a stronger jet stream because of the design having tiny holes to enhance water pressure, right? Water pressure, what this means here, what usually people commonly mean by water pressure of a shower head, right? It means, the force that you feel from the water, right? So don't worry about that too much. It's the jet stream that matters right now. Her roommate, Carly, says that her new shower head won't improve her water stream. Notice how it says water stream. I think, oh, sorry, my headset turned off for a second. I'm gonna have to check if okay, all right, my voice is working again. All right. So her roommate Carly says that her new shower head won't improve her water stream because it's not about the shower head, but it's actually about how fast the water tank can pump the water. Right? Which of them are correct using continuity? Well, Darla is absolutely correct. Why? Because the tiny holes lower the area, right? Where is it? Right here. The tiny holes lower the area, and to have this, and if you're gonna have the same, on both sides, lower area means higher volume. Oh, that's my bad. Higher velocity. So faster water coming out, right? So that is a true statement. If you guys want better shower quality with the water, just change the shower head, right? Which equation could be used to disprove the other person's argument? For this one, I was just looking for, either are you using Bernoulli's equation or are you using continuity? You could have literally taken this equation and wrote it in B and got full credit, right? Because Carly is wrong. It's not about how fast the tank can pump water because that helps the water get to the shower head. That doesn't actually make the water forced out any faster, right? Because that's dependent on the little holes, right? Slightly dependent on the pressure, but I wouldn't worry about that too much. It's mainly the shower head. Okay. Constant volume gas thermometers work by having a fixed number of gas inside that researchers are always aware of. That statement should tip you off that N is constant. Researchers, however, cannot use the ideal gas formula in order to calculate temperature. They must have a modified version, sometimes called the real gas formula. All right. Remember, Mr. Cho went over this in lecture. The two reasons that they cannot use the ideal gas formula is because the ideal gas formula assumes that all particles are the same size. Well, buckos, oxygen is way, way, way bigger than hydrogen, right? So that's out of the box. Or no, that's out of the frying pan. I don't even know what I'm trying to say there. But anyways, the other reason they can't use the ideal gas formula is because the ideal gas formula it ignores the fact that the molecules inside the gas inside can collide with itself, right? If you have enough like gas particles inside of a container, yes, they will hit each other. That's important. They'll hit each other and change up the variables a little bit, and so that's why these scientists can't use those, right? So those two are just things that you need to know. I think I have the months today guide though. If the gas thermometer were to spring a leak, it would cease to function. What variable would not remain constant due to the leak? All right, now there's a lot of correct answers, but I wanted the actual correct answer that is, from the leak, right? Due to the leak. If it leaked, then N would be the first thing to change because then gas particles would be escaping, right? And as a result, the pressure would be decreasing as well. And then, as a result of that, the temperature will be unreadable, right? But people that said that temperature will change, increase or decrease, well, that doesn't matter because you don't know if it'll increase or decrease because it'll just become room temperature at that point, right? So, all right. In the human body, oh, no, another comment. Internal temperature is on average 37 degrees Celsius, right? The lungs typically stay at the same pressure even while breathing, but taking a deep breath in, taking a deep breath, the pressure in the lungs tends to increase, causing pain. Why does this occur? If you try it yourself and just take a really deep breath right now and then try to hold it in with as much air as possible, it'll start, you'll start feeling that little tugging feeling in your chest, right? Now, the reason why this occurs, remember, we're going to use ideal gas law. Temperature is pretty much going to stay constant. So you can just remove that from here thought-wise. And so number of moles, that's increasing. The number of moles is increasing, right? And we know that the volume of the lungs expands, right? However, the amount that the lungs can expand actually goes up to the rib cage. That is the maximum expansion volume of the lungs. Your literal rib cage, which is, holding everything back in like, tight in place. So at some point the volume becomes constant. So the pressure increases. And that pressure, the pressure of the gas forcing on that rib cage and the lungs, all of that just pushing on both sides makes it hurt, right? So that's why it hurts. All right. Now I will go over the extra credit answer. Why is it so difficult to get a breath in when the wind is knocked out of you? All right, this is Poiseuille's law. All right, why is a lot of you guys said, oh, because you have no low pressure in the lungs because it's knocked out of you. Actually, that's incorrect. The pressure inside your lungs is actually extremely high. If you had a low pressure, Poiseuille's in your lungs, Poiseuille's law states that air would easily flow from high to low, so it'd be easy to get a breath. But it's hard to get a breath because that volume, the volume is, there's a set amount of volume that the lungs can shrink to, right? And then all the air left. So that means that because all the molecules of air are gone, all the wind got knocked out of you, that pressure is going to get extremely high because the volume is going to shrink, right? And the pressure is going to be high. And therefore, it's so much higher than atmospheric pressure, you just have to wait for it to, diffuse and equalize as the lungs slowly expand, right? So that's why it's so hard to get a breath in. So if you do ever get the wind knocked out of you, your first order of action is to try to assess the situation. If you're in a panic situation, it's going to be a lot harder. But if you just fell or something, Mr. Cho knocked the wind out of him when he fell off the playground once, and it was really painful. That was not when I'm 23, but when I was like 10, right? I don't know, maybe I was like 12, who knows? But I definitely did not know this method. What you're supposed to do is you're supposed to relax your muscles so that your lungs can naturally expand faster, all right? And that'll make sure the pain goes away fastest. So there's a little quick tip for you. All right. So that was this series of worksheets, right? If you have any questions on those, you can rewatch the video with timestamp or just email me and then I will go further into explanation. If you have any questions on the study guide, I will have office hours tomorrow from, let's say, probably from noon to 1, but we will see. All right, I'll make a Google Classroom post on that. All right, so enjoy the rest of your day. Have a wonderful time. All right, good luck on the exam.